Uh, is a third-year PhD student in theoretical neuroscience at Columbia University in New York, and he's working with Larry Abbott. And today he will talk about using RNNs for dynamic binary classification. Welcome, Dennis, on stage.
Okay. All right, good. Can you hear me? Okay. So yeah, thank you. Thank you for being here to listen to the talk. So thank you all for tuning in. I'll describe an alternative solution to the classical binary classification task, an alternative which is more realistic than typical models. The perceptron well studied for this task is effectively a set of n neurons, each of which receives some direct input and then project to an output neuron whose job is to decide the class of the input. Typical daily binary decision tasks include things like, do I do my yoga today or skip it, or do I eat the Halloween candy or pass it this time? And these decisions require sensory perception, cognition, language, motor commands, and even spatial reasoning. So these brain functions are highly linked with the neocortex, a brain area which is highly recurrent and very sparse. And unlike the neocortex, as seen in this diagram, the perceptron is not recurrent, is fully connected, and also has a highly convergent output neuron. So with this in mind, I used a new architecture to solve this relatively simple task. I maintained a similar structure for the input as well as for the output. The only exception is that the output is now very sparse, and I replaced the whole perceptron architecture with a highly sparse recurrent neural network to better model the neocortex. This RNN is truly very sparse, and connections are not symmetrical as suggested in this graph, where some connections are missing, but not all. And I will shortly describe this argument of the final or output sigmoidal or thresholding function to understand this RNN's computation. But before, I want to show that this network can achieve maximum performance with the backpropagation through time. So here, input is shown to the network for a period of 10 time steps, and then it is turned off. And this plot shows performance of the network at each time point, at each stage during training, where one can observe that as training advances, it learns slower and slower until it eventually hits 100% accuracy. So to understand how this network computes, I'm showing the output activity of the RNN for inputs from both classes, red and blue, as depicted here. It clearly shows that this RNN differentially amplifies the signal from one class and suppresses the signal from the other. An additional thing about this architecture is that it can successfully classify approximately as many random inputs as it has learnable synapses. And learnable synapses in this case is sparsity times n squared, the number of connections in between neurons which are learned with the backpropagation algorithm. And here I'm showing the mean in blue and the extremes in orange and green of accuracy as a function of memory capacity across multiple simulations. Just to summarize what the memory capacity of this network is, and to demonstrate that training is stable and reliable and avoids catastrophic issues such as catastrophic forgetting. So with high sparsity that I'm using in this network, the recurrent network will eventually disconnect according to the Erdős-Rényi random graph theory. And here in gray, I'm showing the probability that a graph of size n for different values of n is connected. And simulation results for an RNN of size 100 are shown in blue. So I want you to observe here that performance for this RNN is starting to be affected right about at the intersection in between the blue curve and the n equals 100 gray line. And the orange line is similar, but for an RNN of size 200. So how I studied this slightly further is basically when I take an RNN above percolation threshold, so I generate a random graph whose adjacency matrix is connected above percolation. And then I manually disconnect it by building effectively five smaller random networks of the same overall size. Performance drops, as you can see here, with this color-coded symbols. So then, interestingly, when I take an RNN below percolation threshold, so this adjacency graph here is not fully connected, and then manually connected in these two highly structured ways, performance also drops, which this was surprising because the expectation was that a connected network would perform better, but structuring the connectivity is very important as well. And I'm showing that by taking a different RNN, also below percolation, but then I manually connect it, preserving as much as the graph's random structure as possible. And in this case, performance increases. So it is not clear what random structure is important for high performance, but graph connectivity proves to be very relevant and allows the RNN to distribute information through all neurons despite the high sparsity. And here I introduced two separate Gaussian noises to the RNN just to show robustness of the architecture. Dynamical noise, which is geared towards the recurrent dynamics, and input noise. And I'm showing that RNNs of different sizes, different memory capacities, and different sparsity values exhibit lots of noise robustness. So in this yellow region here, basically you can have some noise in the network and it doesn't really affect performance. And also generalization accuracy decays in time slowly outside the training period in which backprop through time operates. And importantly, the two noise types that I'm suggesting here, though maybe a bit obscure, the two noise types sublinearly affect performance. And unsurprisingly, dynamical noise here, you can see it decays slightly faster in the generalization regime. And here I'm showing that this table shows that the architecture is also robust with respect to various activation functions and activation functions in the recurrent layer, and also to various loss functions that backprop is optimizing. It has some favorites, like some of these values are better than others, but we have a slight idea why this happens. But overall, it's quite robust. And finally, when neurons in this network have strict excitatory or inhibitory identity, performance decays rather naturally and not catastrophically. So the symmetry in the task, in the input shown to the task, reflects here in the symmetry of this excitatory and inhibitory plot, in which if you have too much excitatory neurons compared to inhibitory neurons, performance slightly decays. And though this is not perfectly symmetric plot, it shows a slight preference for having more E neurons, and we do not know yet why this is the case. But compared to an unconstrained recurrent network, the performance is effective naturally and then quite as estimated. So in here we have a capacity of alpha 1. It's equivalent to a similar network, unconstrained network, which has a capacity of 1.6. Which can be estimated with some simple calculations as well. So to summarize, a highly sparse recurrent neural network can solve binary classification dynamically and distributively, making complete use of all of its neurons. It integrates input and maintains a decision for a long time by differentially amplifying its activity for different input classes. And for top performance, according to the Erdős-Rényi random graph theory, each neuron only needs on the order of logarithm of n connections to other neurons, which makes it a very, very sparse recurrent architecture similar to the neocortex. And with that, thank you, and thank you to my advisor, Larry, and all the funding sources. Thank you.
Thank you very much, Dennis. So while we wait for some questions from the audience, there is Friedman Zenke is raising hand. So let's see.
Hello there. Can you hear me?
Yes.
Yeah. Go ahead.
Thanks for the talk. I have two questions. So first question would be, did I understand correctly that the topology remains fixed throughout the simulations? And the second question is, did you look into the dynamics of the network, and can you say anything about which mechanism actually amplifies or suppresses the solution?
Yes, to your first question, yes, the topology remains fixed. So basically, there's a highly sparse mask, 0 or 1 mask in the adjacency graph. So we do not modify connections. New connections between neurons cannot appear or disappear in the network. Can you please say again your second question? I'm not sure I understood your.
Yeah, I was wondering whether you analyzed the emergent connectivity, like look at the spectrum of the emergent matrix after training, and whether you looked into what's actually amplifying the correct solution.
Oh, I see. Yes, but only slightly, and it's not really clear what happened. So initially, we would expect to have in this plot, for example, we would have expected to have perhaps kind of two fixed points regime, in which one of the classes kind of goes to one fixed point and the other goes to the other fixed point. But what seems to arise naturally, at least, is you have some sort of slight amplification, and after this time point, basically everything slowly decays, which is reflected in this accuracy plot here. When you see when the decay starts to happen, basically the red curves and the blue curves start overlapping, and then you lose accuracy. So it's not entirely clear, at least to us, exactly what happens.
Cool. Thanks, Friedman, for the question. Is it?
Yeah, I can keep asking more questions, but maybe other people have questions too.
Not for now, so go ahead.
Yeah, go ahead.
Yeah, so then one more question about the topology. Did you think about maybe approaches of whether you could optimize the topology, as this is done lately a lot, and also we've seen in the previous talk, and whether this would then maybe naturally lead to a fully connected graph, or?
Yeah, I see. No, the short answer is no, I didn't look at that. The main reason is that for now, at least, the purpose of this work has been to kind of understand if a recurrent network can really use its information like distributively if it is sparse, without assuming a special case of highly convergent neurons. So, if you start optimizing the topology, you may end up having a few neurons that require a lot of connections. And we wanted to keep things rather uniform. So here in this slide, when I say that you only need on the order of logarithm of n connections per neuron, we kind of that's a goal of the project. We don't want to have kind of rare event neurons which are highly connected. So we didn't look into that. We wanted to have kind of a uniform picture of the topology. Yeah.
Right, makes sense. Yeah, I find it very surprising that the dynamics are the way you showed, that they're not diverging to a fixed point, and that you basically have transients built into the dynamics, right? Usually you would imagine if you had a low rank connectivity, yes, you would get a fixed point at high activity and one at low activity, but that clearly doesn't seem to be the case. And I'm trying to parse in my head where this could come from, because it clearly looks more brain-like that way, but yeah, very interesting.
Yeah, that's what we're trying to do as well. To be honest, it may be due to the specific type of loss function and training that I'm doing. So this here I didn't mention during the talk, but these black lines are some targets that are used for training. So the red curves are pushed by backprop to exceed this black line, and they are penalized if they are below this top black line. And likewise for blue curves, they are pushed to be below the lower black line, and they are penalized only if they exceed that. So that's why we kind of are able to create this gap to differentially amplify between those, but this is a purely simulation result, and we don't have an analytic understanding of why that happens yet.
Right, but the stability is then baked into the learning algorithm somehow. Although the red one, I suppose, could still go off to high activity, and you wouldn't prevent it from doing that.
Yes, that wouldn't prevent accuracy going down, but for some reason it doesn't happen in simulations. It doesn't explode off here. They all turn back to decay back to zero.
Mm-hmm. Okay, thanks, Friedemann, for your questions. We actually have one more question before we finish very soon. We have a question from the YouTube stream. How cool is that? That's by Daniel Hernandez. Thanks, Arash, for passing it over. So they're asking if it would be possible to implement this in real time.
The learning rule takes a long time to train, but once you have the network, it's incredible. It's very fast to make the decision. So learning will take a long time, backpropagation through time in this case. But once you have it, it's effectively instantaneous.
I see. Okay, cool. Okay, so if there are no more questions, I think we can finish here because there's another session starting very soon in 2 minutes. So thanks everybody from the audience for attending, and especially thanks to the speakers, Thijs, Mathilde, and Dennis, for your great presentations, and I wish you a lot of success and luck in your future research. And thanks, Arash, as well, for doing a lot of great work in the background. Thanks, everybody. Have a good day.
Thank you.